Welcome to lecture number 15. So, we will continue from where we left off, but let us reconstruct where we left, what are the things we have learned so far. So, what we have learned so far, very quickly a summary of that is that here we have a conduction band and here is a valence band edge and conduction band edge. This is the band gap Eg of a semiconductor. If that is the case, then number of electrons per unit volume in conduction band is Nc times 2 over root pi Fermi direct integral of this quantity eta c, which we have defined. Likewise, P is equal to Nv times 2 by root pi Fermi direct integral of order half eta v. Again, eta v is defined, but if semiconductor is non-degenerate, meaning thereby if the Fermi energy lies between the 3 kT away from either of the band edges in the band gap, then in that case we can also approximate n as Nc e to power Ef minus Ec by kBt, P as kBt Boltzmann constant, Nv times e to power Ev minus Ef by kBt. Then also we introduced the idea of intrinsic carrier concentration Ni, that Ni, in terms of Ni we could have written the same relationship in general for whatever the whether it is semiconductor is intrinsic or not. We can always write this as N as Ni e to power Ef minus Ei by kBt, P as equal to Ni e to power Ei minus Ef by kBt. So, if we define this quantity Ni, then we can write N and P in this form also. Other thing we learned was, as long as semiconductor is non-degenerate, product Np is always a constant, and that is equal to Ni square. That is another thing we have learned, and this quantity of course we have learned is equal to Nc Nv e to power minus Eg by kBt. This is another thing, another relationship we learned, that product Np is constant. This matter Np equal to Ni square does not matter, it is always true. So, this is always true. This may be, it is worth looking at. Let us come back to this in a minute, but before that let us finish everything else, and then we also determine if semiconductor is intrinsic, then whatever the Fermi level, that is called Ei, and that is equal to Ev plus Ec by 2 plus 3 by 4 kBt log of effective mass of hole by effective mass of electron. So, these are the few relationships we learned, and only thing is intrinsic semiconductor means, and then we said intrinsic semiconductor means N equal to P, and that concentration we gave it a name called Ni, and Fermi energy whatever in that case is, that is called Ei. So, you see, and we then went on to determine what Ni value will be, and then we ended up plotting that as well. I want to spend few minutes talking about this product Np equal to Ni square, which is constant. That means, let us think about this Np equal to constant, and that constant of course is Ni square, because in a special case when N is equal to, when intrinsic case when N is Ni and P is Ni, then this constant will become Ni square, and since it is a constant, it will always be true. Therefore, Np is Ni square. But anyway, the point that Np is a constant, what does it mean? It means as follows. There is always a continuous, you can think of in terms of a chemical reaction with which you are quite familiar. Recall equilibrium constant of chemical reactions. So, if we write a reaction like thing for electrons and holes, then we could think of a equilibrium situation and see what the law of mass action will be, for example. What I mean by that is, what is constantly happening, so when I say that there is a certain number of electrons present in the conduction band, what does it mean? It means that constantly in this material by some process, some electrons are jumping from valence band over to conduction band. This is a process by which carriers are generated. That means, for every electron that jumps from valence band to conduction band, I get an electron and a hole pair. It creates electron in the conduction band. Simultaneously, from where it left in valence band, it creates a hole. So therefore, I get a hole and electron pair essentially as a process, what we call as generation, process of generation. Then what happens is, some of the electrons which are now in excited state, they want to return back. When they return back, what do? Electron and hole, they recombine and annihilate each other. They leave nothing. That process is called recombination. So if I look at it as follows, if I look at this reaction as follows, that N plus P goes to nothing. In other words, if I think of it like this, or let me write it here, that if I think of like this, that N, I write a chemical reaction which is like this, where this process of N and P is recombination, and this is a process of generation which I have shown pictorially there. Up here I have shown pictorially. So now what is it? From generation processes that I have nothing, or if you think I have an electron and I have an electron sitting in valence band, but suddenly what I did, that once the electron jumps to the conduction band, that means it goes here, here is the electron in conduction band, it simultaneously leaves a hole in the valence band. That is the generation process. So this left side going from right to left, therefore is the generation process. And simultaneously, at all times, this N which is in conduction band and this P which is in valence band, these electrons, holes in valence band, electrons in conduction band, they are recombining. That process is R, going towards the right. That recombination, when it happens, electron and hole pair is annihilated. That annihilation is shown in the right when the reaction goes to right. So you think whatever the electron concentration here is and whatever is the hole concentration here, that is a result of an equilibrium between these two processes of recombination and generation, and in it at some temperature. If so, then you can see that this equilibrium will be established when the rate of forward reaction is same as rate of backward reaction. So what would the rate of forward reaction will be? Rate of forward reaction will be something, rate of forward reaction will be some constant Kf, let us just name it Kf as the constant for forward reaction, multiplied by N and P. So we think of rate of reaction as some constant times product N and P, which will depend on how many electron holes I have, and accordingly the recombination will depend on that. That rate should become equal to rate of backward reaction. The backward reaction, of course, is just some constant, because remember 0 goes to N plus B. So it depends on the right hand side only. So that is rate of backward reaction. What does that lead to? That says that NP is a constant. So you can see this result is not unusual result, in the sense that it follows exactly like what you have done for chemical equilibrium. That is exactly what you do. Rate of forward reaction becomes equal to rate of backward reaction, and then a chemical reaction is thought to be in thermal equilibrium. Exactly same analogy applies here of equilibrium between electrons and holes. So with that, let us move forward. So that's what we have been doing till last time. Now what I am going to do is move on to extrinsic semiconductors. I have talked about intrinsic semiconductors. Now let us talk about extrinsic semiconductors. Extrinsic semiconductor, that is what we want to talk about, or you think of that as doping, the doped semiconductor. You think of that as a doping. So let us ask a question which is very typical question. What will happen if we add a few phosphorus atoms in silicon? What will happen? That is the question we ask. All right. So when we, first of all, phosphorus atom goes on substitutional side. It goes on substitutional side, meaning thereby I have a lattice. silicon atoms sitting on these lattice positions. When I add phosphorus, essentially phosphorus is replacing some of these silicon atoms on their site, and phosphorus occupies the site which belongs otherwise to silicon. That is called substitutional site, and so phosphorus is a substitutional atom. It is not necessary, however, that all atoms or impurities, consider phosphorus as impurity, small amount added in silicon. The small amount of impurity that we are adding in silicon, it is not necessary that it always goes to substitutional site. It is possible that it goes to interstitial site, for example. That is also possible. It is possible that we may not add impurity atoms at all, except that there are some vacancies or interstitial of silicon atoms itself. All these defects could also be there, and they could act like impurities. How, that we will see. So, our description is going to be more generalized, but phosphorus and on substitutional atom only forms an example, just an example. So, what happens? This is a standard approach we take, that in the outer shell of phosphorus I have essentially 5 electrons. These 5 electrons are there, whereas silicon has 4 electrons, and silicon undergoes this bonding with other covalent bonding with other silicon atoms. Now, if we replace one of this silicon with phosphorus, so if I have phosphorus here, then 4 of these electrons of phosphorus of course take part in bonding with the silicon atoms, but then I am left with one more electron, the 5th electron. I am still left with the 5th electron, which in this picture is bound to phosphorus. In this picture, this electron is bound to phosphorus. All right. Now, what happens if I raise the temperature, for example, or you think like this, that this 5th electron which is bound is being screened by other electrons, and hence is very loosely bound. It is very loosely bound. That means it can easily be taken away from this phosphorus. So, that is essentially the picture which we want to see, say that 4 of the 4 electrons of phosphorus have gone into bonding. The 5th extra electron, let us do it like this again. We have EC, we have EV, that is the band edge. We know that if there was no impurity atom, then we would have had to break this bond, and then an electron from here would have jumped over to here and gone here, and leaving a hole behind here. That is the picture we have been talking about in intrinsic semiconductors. Now, when you have phosphorus atom, this 5th electron, since it is being screened by rest of the electrons, so it is very weakly bound to phosphorus atom. I can think at this point in this picture I am showing that phosphorus is bound. That means I can think of it like this, P plus as an entity which is phosphorus with 4 electrons, and since phosphorus is neutral when it has all the 5 electrons, so that is why I am showing 1 plus charge, since the 5th electron is and then I am going to show the 5th electron like this. So, there is 4 electrons which have gone into bonding, and that we are calling as P plus with 4 phosphorus is 4 electrons, and the 5th electron is right here. Now, how much energy, question we ask is how much energy we require for this electron to become free, this 5th electron to become free. Clearly, since it is being screened by electrons, it requires much less energy. The way we do it therefore is as follows, that we show in this band gap where there are no states, in this band gap which is shown here, in this band gap while there are no states, artificially we show a level like this which we call as the donor level, a donor level, we call it donor level where the 5th electron sits. So, if I wish I can talk about like this, that here is in my picture, then I will show something like this, a plus and a dot, 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 plus dot, plus dot, etc. and a dot. What that means is plus is indicating this phosphorus plus and the 5th electron. So, we think that there is an energy level like this, we think it is a hypothetical energy level, you think in relative to EC. Then if I have sufficient energy Sufficient energy meaning only energy which is this small, EC minus ED. If you have such small energies, in that case this fifth electron could simply jump and get here in the conduction band. All these fifth electrons could therefore come and jump here. That means I will be left with what I have will therefore be a phosphorus which is neutral, means it is tied to it has 5 electrons. What is happening is that it is becoming P plus, which is phosphorus with 4 electrons which have gone in bonding, and the fifth electron which is very loosely bound, it goes into the conduction band by having room temperature is adequate enough that all these electrons can easily go to the conduction band. Once the conduction band, as you know, conduction band means where electrons are free to move about, they become like almost like a free electron, so they can move around in that. So that is what is meant by, so you can clearly see if I add few atoms of phosphorus, I can therefore increase number of electrons in the conduction band, because this fifth electron will be loosely bound and it can give electrons to the conduction band. All right. Now such dopants are called donors, because they are giving away electrons, they are donating electrons to the conduction band. So they donate electrons to conduction band, and hence we call them donors. In general, we will give them a name D, and in silicon, for example, a list of such donors will be phosphorus, arsenic, phosphorus and arsenic and antimony would be some examples which are group 5 element, because they have 5 electrons. Let us also talk about, for example, acceptors now. Let us talk about acceptors. By analogy, therefore, acceptors would be those which will accept electrons A. An example I will take is, for example, boron or aluminum, which are group 3 elements, So let us start talking about acceptors. Now think of boron. Now this boron only has 3 electrons in outermost shell. See, if I take this silicon atom in bonding, again I show the same picture, and replace this central silicon atom by boron, but boron had only 3 electrons. So how do I complete all these? So if this were like this, then we are okay. That means 3 electrons from boron, for example, are participating in formation of bond. But then I have not completed the covalent bonding. I need this bond as well. How does that happen? So we conceptually imagine that this happens as follows. That again a picture like this, where I have a conduction band edge, valence band edge. We think of valence band having large number of electrons. We think that now boron is going to borrow an electron from valence band, because valence band is full of electrons. So it is going to borrow an electron from the valence band and complete the bonding. When it does so, then essentially there is a hole left behind in the valence band, that we show as similarly a acceptor level. And this energy difference EA minus EV then indicates the amount of energy required for this electron to be taken from the valence band, and boron can complete its bonding, leaving behind holes. So essentially, therefore, once the electron goes here, since it accepts the electrons from the valence band, it leaves holes behind here. So you can see that just like phosphorus in silicon, boron is capable of creating holes in the valence band and contribute to P in valence band. So we can change the number of P, that is number of holes per unit volume in valence band, by including in material a group 3 element. All right. So these, and as the name suggests, that this should therefore be called acceptor, because they accept electron and thereby creating a hole in valence band. So that is the picture we would like to have, except maybe I give you some more examples in this case. So, for example, if you are interested in gallium arsenide, then I can name some donors in here. Donors could be, for example, silicon is a common donor in gallium arsenide. Now, this would be a more interesting example. Now, you see silicon has 4 electrons in outermost shell. If silicon goes and look at gallium arsenide. So, let us consider this example also, it is a pretty interesting example. Gallium is a group 3 element, arsenic is a group 5 element, and silicon is group 4 element, and I am saying that silicon is a donor in gallium arsenide. What does that mean? That means that silicon must have a preference to go on gallium side. Only then, if silicon has a preference to go on gallium side, which let us indicate like this, that gallium is the site and silicon is sitting on it. Imagine like this, in notation I will use is gallium sitting on gallium side, arsenic sitting on arsenic side. This subscript is indicating the site, and the atom on that site is also indicated there, which is gallium on gallium side and arsenic on arsenic side. Now, suppose silicon is a substitutional impurity and 2 possibilities exist. Silicon could go on gallium side, which means I will write it like this, or silicon could go on arsenic side, which means I will write it arsenic side and silicon sitting on that side. Clearly, if silicon goes on gallium side, since it is a group 4 element, it would have an extra electron, and hence it can be a donor. Whereas, if silicon goes on arsenic, which is group 5 element, then it could behave as acceptor. The thing of it is that silicon indeed in gallium arsenide goes on both these sides, gallium and arsenic sides, except it has a preference to go on gallium side, and more of silicon goes on gallium side than it goes on the arsenic side, and hence the net result is that silicon behaves as donor in gallium arsenide and is a pretty common donor in gallium arsenide. Similarly, acceptors in gallium arsenide, let me give some examples, could be zinc, for example, carbon. Carbon is an acceptor which normally is present anyways in gallium arsenide. When you make gallium arsenide, it behaves like an acceptor. Remember, this is also group 4 element. This is also group 4 element carbon, which means it has a preference to go on arsenic side. That is why it is behaving like an acceptor. Zinc, on the other hand, is a group 2 element, and hence clearly it can behave like an acceptor. These are the few examples, or few more examples you can look up in any book, or any textbook, or any database. Now, acceptors and donors for different materials. But what I want to say, the next thing is that all these materials I am talking about, all these dopants I am talking about, are what we call as shallow donors, shallow dopants. Meaning thereby that if it is a donor, then EC minus ED is very small, on order of 10 millielectron volts, something like that, maybe 30 millielectron volts, maybe even 100 millielectron volts, but that is shallow. And if it is acceptor, then EA minus EV is 10 millielectron volts or so, on that order, or maybe even 100 millielectron volts, in that range, 10 to 100 if you wish. 10 to 100 millielectron volts is the order in which they are. So, these are we call as shallow dopants, because room temperature KT energy is sufficient. KT at room temperature, as I have said, is about 30 millielectron volts. It is sufficient energy to promote these electrons either to conduction band or to accept the electrons from valence band. Electrons from valence band can easily jump to EA level if these levels are shallow levels. So, if these are levels are shallow, and shallow meaning that the energy difference is small. So, these we call as shallow dopants or shallow level impurities. There is a little difference between dopants and impurities. I suppose you can distinguish them by saying impurities are those which have gotten added out of control. That means you did not, they are not intentional, they are just there, but you did not deliberately put them. Whereas dopants would be those where you deliberately add them to manipulate your N and P. So, that is what we will call as shallow levels. Since I have introduced the name shallow levels, it is worthwhile to introduce also what is called as deep levels. So, the name suggests that these deep levels are also, the deep levels are something where this energy will be large. So, if I have like this, EC and EV, then if the dopant level, let us say donors lie and acceptors, if the donors lie somewhere deep, large EC minus ED, and this is ED level, or acceptors are somewhere in the middle or even higher towards the EC, a large then these are called deep levels. And clearly they are deep levels because this energy difference is large. If this energy difference is large, then you can see that thermal energy may not be enough to completely ionize these defects into either cannot ionize the dopants and to promote the electrons to conduction band or to accept the electrons from the valence band. Notice that we have written here D as when D has its electron bound to it, we are going to write it in 0 charge state. That means charge state is that since like phosphorus has its 5 electrons, then 0 charge state, it ionizes, then it goes to D plus, that means phosphorus plus with 4 electrons and an electron. Similarly, I could write here acceptor as acceptor like a boron with 3 electrons has 0 charge on it, because boron comes with 3 electrons. So, that is why that is a native configuration. So, that is no net charge on it, boron when it has 3 electrons, but when it accepts electron because it wants one more electron to complete the bonding, it accepts one electron, then it becomes ionized and it becomes A minus, for example, it becomes A minus. So, that is what I mean, that if deep levels, if the levels are deep, then room temperature may not be sufficient for this acceptor to accept this electron, because it requires this much energy to accept the electrons and EA minus EV amount of energy. So, it may not be able to accept, or very few may be able to, and therefore, very few of these dopants may ionize in that case. Similarly, this energy difference EC minus ED may be large, and therefore, this dopant may not be able to ionize to D plus state, thereby giving the electron to conduction band. It may not happen, or if it happens in very small quantities. These are therefore deep levels. Deep levels are many, they have good use and they have bad use. For example, if you add in silicon, if you add copper or gold or iron, all of these form deep levels. What that means is that these are not going to, so they are lifetime killers. That part will be taught to you a little bit in future, few lectures down the line. It will be taught to you when we talk about how the statistics of recombination of these carriers is, how the carriers are generated and how the carriers are recombining. So far we are saying that recombination and generation rate are equal, that means they are thermal equilibrium. Then what is the condition? But when we individually start looking at recombination and we individually start looking at generation process, then we will use this concept of time also. But the point I am trying to make is this deep level, because once the electron gets in there, then since its energy required to ionize is so large, so it may not ionize easily, and hence it is called as a trap level. That means it traps the electron, it sits, once it gets it, it holds the electron. If so, then what it may happen is that it may happen that the carrier may not be available for conduction. So, that is the bad news. The good news is, that if you have them, then they become the centers where the recombination may happen. The electron can come at this center and holes can come at this center and recombination can happen. Why that happens? That it has a large cross section, that these aspects you will understand later when it is taught to you. However, these deep levels do have a use, good use and bad use. If you are making a silicon device, for example, you will ensure that wherever you are making, there is no scope of copper, gold and iron, these kind of materials reaching there. Similarly, so these are called deep levels because the energy levels are large and they act as traps for electrons. Because they are traps, therefore they can suck up your electrons and not let it participate in conduction. On the other hand, it may provide the level where they suck up electrons and holes, and hence therefore provide a level where this electron and holes can physically come together and recombine with each other. So they have good role and bad role to play, which you will learn little bit later. So with this, let me move on to the next topic. So we have these dopants added. How do they ionize? Ionization of dopants. In general, what you can do is we can write some. We could have derived this equation, but in this class we will not do that. Let's imagine like this. Suppose you have an ionization reaction going like this. That I have any dopant, a donor dopant. Let's call it D. D goes to exists right now in charge state n plus. This n plus may be equal to 0 also, so n may be 0 also, as I have written in my example earlier. And what it happens is that it becomes D one additional charge state, positive charge state plus a electron. Suppose this happens, or so if this happens, then without deriving, I will give you an expression saying that number of I will just define the symbol in a second. The ratio of these two, not x but rather D I would write, exponential of so this energy EV, EC and EDN is this energy level. EDN is that energy level which is indicated there. Then we say that fraction, you think of this as a fraction. We think of this, let me try to explain this in a minute like this, that this is number of D n plus 1 plus kind of species per unit volume divided by number of sites for this D per unit volume. This is what this quantity is. Similarly, this quantity therefore will be equal to n D n plus divided by n sites, meaning thereby that this is the number or number of if this is the consider for example phosphorus atoms. So if you think phosphorus is going on substitutional sites of silicon, then this is number of phosphorus atoms which are in fact let us choose this as example. Suppose n is 0, n is equal to 0 here, this n charge which I am showing is 0, implying therefore imagine this D0 or donor D is going to D plus electron. Then this quantity D0 would indicate that this will be number of D atoms in 0 charge state divided by number of sites D can go per unit volume, of course, both are per unit, same basis, per unit volume. Number of sites for D atom, for example, if it is in silicon, then it is number of possible sites for silicon atom. That is what it means, number of silicon atoms per unit volume. Number of silicon atom sites per unit volume is the denominator, and numerator is number of these phosphorus atom d atoms per unit volume. So, in that sense, then if this number of sites are the same in both cases for these defects, they both are silicon sites, in that case this ratio also indicates ratio of number of. So, I can write this whole expression also as number of d n plus 1 in plus side state, number of d in n plus state as being equal to same exponential, which is E d n minus E f by k b t. So, there is a number per unit volume in this state and in this state. Ratio of these two is given by this particular expression. That is the ionization, how the ionization occurs, how much is ionizing from ratio between one state to other state. Now, let us continue. Now, we will next go to acceptor behavior. So, similarly, let us write down for acceptors also. If we have a acceptor reaction which is going on like this, let us say x of in n minus 1 charge state goes to it accepts electron, it takes electron and goes to n one more additional charge state, n plus 1 negative charge state. If so, then number of, by same token, number of this species A n plus 1 minus per unit volume number of A, this n minus ratio of this then is simply given by exponential this is the ratio in which the ionization occurs. All right. With this, let me now restrict my attention to monovalent impurities. Or dopants. As far as we are concerned, it is the same thing. Dopants are intentional, impurities are unintentional. What do I mean by that? When I am writing this n minus n plus, what I mean is there are impurities, for example, sulfur, which could go to S minus 1 state, it could from S minus state, it could go to S 2 minus state, it could go to the second electron also and get 2 minus state also. These are multivalent impurities, and hence we have been using this symbol N. That means sulfur from minus 1 state accepting one more electron and becoming sulfur 2 negative. That kind of acceptor level also exists, which is why I have given you more general expression. But if we are talking about monovalent impurities, in that case what we mean is that exactly one ionization occurs. That means we either have donor in in neutral state and that becomes in plus state and gives the electron, whereas acceptor in neutral state accepts electron and gives you a minus state. This is a monovalent because there is only one ionization level from 0 to plus 1 or 0 to minus 1. In general, from any charge state to another charge state different by only 1, and that is only reaction possible. No other reaction is possible. That is what is meant by monovalent impurity dopant. If so, then we will restrict this, we will write our expression back again. For donors, we had in the plus extra charge state divided by in the original charge state. So, we will write this as d plus. So, we can write this as, now we will use this different symbol. I will use capital N now, which is more commonly used in this case, n d plus divided by n d in 0 charge state should be equal to e to power, I am using this formula here, e to power E d minus E f. So, E d minus E f by k b t. And similarly, I am going to write here, and this small, I am using the same small n instead of small n, I am starting to write capital N, which is number of d plus type of at d plus ionized atoms, for example, phosphorus, if you are thinking, number of phosphorus atoms which are ionized, which have given its fifth electron. So, they are only left with 4 electrons. That's so a question asked is that if this was phosphorus, then it would have given P plus an electron, some phosphorus retaining its fifth electron, and some electrons have been given away by phosphorus, and hence it is in P plus state. So, and then question asked is what is the ratio of the two, how much are they, number of them per unit volume, and that number is this capital N I am showing you, number of such state, number of atoms in such state, impurity atoms in such state per unit volume. Therefore, similarly using this expression I can write number of A in minus state divided by N of A in 0 charge state should be equal to e to power E f minus E a by k t. Now, let us make a picture of it and then see what it means. What it means is as this. So, I have this is E c and this is E v. Let us say that I have certain acceptor levels. So, let us show them those acceptor levels right here. And I also have, and some of these acceptors which are shown here, some are in 0 charge state, that means they are not occupied, and some have taken away their electron, they have taken its electron, some are having electrons, they have accepted electrons, meaning thereby that I can indicate them as A minus, and this is state is A minus and this state as A minus, whereas the ones which have not accepted the electrons are in state A 0, A 0, A 0, A 0, and this is E a level, and total number of such states, number of acceptors I have added, let us say is N of A. That is the total number of, I am showing here 1, 2, 3, 4, 5, 6, 7 acceptor states. So, I am thinking of N a as being 7, and this quantity of course being equal to what is in 0 charge state plus N a in minus charge state. These are the two charge states they exist in, and we already know what the ratio of these two are. How have they, what is the statistics of this ionization process. Similarly, we think of this as the donor level, and in the donor level I think of some sitting bound to the electron, some electrons are bound, fifth electron in phosphorus for example is bound, here is like this, and in some cases electron has been given away. Electron has been given away. So, this is E d level, this is E d level, and I have total number of such in this example shown 1, 2, 3, 4, 5, 6. Total number of donors like phosphorus atoms that I have added are 6 for example, and some of them have ionized, that means they have N d plus, meaning thereby here it is, this one is ionized. So, this is N d plus and this one is ionized. So, this is N d plus, because it has given its electron to the conduction band, whereas and some of them have not given their electron. So, they are still in 0 charge state, net charge state is 0 plus n with the electron there, fifth electron. So, this is N d 0, this is N d 0, this is N d 0, or I should not say N d, my mistake, let me. So, this is not N d 0, but d 0, this is d plus and this is d 0 and this is d 0 and this is d plus and this is d plus, the ones which have given away their electrons. I hope that gives you idea of what these statistics are. So, here is one statistics, that means the ratio in which these two are present are given by this, ratio in which this and this are present is given by this expression. Okay. So, if so, our question becomes back again, all right, let us just manipulate this little bit more, let us just copy, write down these statements one more time, and continue on this for a few more minutes. Nd plus divided by Nd 0 as equal to e to power Ed minus Ef and Na minus this Na minus divided by Na 0 as e to power E f minus E a by K B T. All right. If so, also I know that N d is equal to N d 0 plus N d plus and N a is equal to, this is total, this is the amount I know I have added, this is the amount that I have actually added, and I am asking the question how are they split, whatever I have added, how much has given its fifth electron here in this case, and how many have not given their fifth electron. Similarly, when I add so much acceptors, how many have accepted electrons, which is this one, and how many have not accepted electrons, which is this one. How many are these? That is what we are asking. So, sum of the two therefore is 0, is Na. If so, then what we will do is that instead of this ratio, we will use this expression and we are going to write this as therefore Na Nd. So, we eliminate Nd 0 in this and instead write we will eliminate Nd 0 in this. So, I am going to write this as Nd plus divided by Nd minus Nd plus as equal to e to power Ed minus Ef by Kbt, which I am going to write therefore as inverse of that Nd minus Nd plus divided by Nd plus as e to power Ed minus Ef by Kbt, and this I am going to write this as Nd divided by Nd plus equal to 1 plus this quantity right here, this quantity right here, yeah, and then this is going to, let us just carry out this. So, and then take inverse of this. If I take inverse of this, therefore, I will write Nd plus by Nd, therefore, the total amount that I have added, what fraction of total amount has ionized, that is the question we are asking, should be therefore equal to 1 divided by 1 plus e to power and by same token, similarly you would get an expression where we would write this as sorry, when we write this, invert this. So, in that case mistake here, an error here. When we invert this, then we should have written as this as Ef minus Ed is what I should write here as Kb, and by same means, same way Na following this Na minus by Na should be, this is the total Na now, total Na should be equal to 1 by 1 plus e to power Ea minus Ef by Kbt. All right. So, this is the fraction of total which I have added, how much of that has ionized, that is what this therefore indicates. Now, you would often sometimes see, not often, in some books you will find a factor included here. For example, I am going to write it with some blue pen, that a factor something like 2 or a 4 added here, the factor of 2 or 4 added in here. This factor you could add, but I do not want to get into this I do not want to add, this has something to do with the spin available, and this has also something to do with, this is a degeneracy of the levels, this is something to do with the degeneracy. Remember, valence band, split off band and a regular band was coming very close to each other, something to do with this fact which I will not include in this course. Once I add this, if it is truly there, then what I can do is I can express this 4 as exponential of something quantity, whatever that is, exponential. I can take it inside this E in here and include it in EA and write this as an effective EA. I can proceed this way, and therefore effectively I can remove what is in the front. So, as long as you imagine this, so I am not going to add this in here, I have decided to remove it, I will leave it at that. In some books, if when you read, you will find a factor in front of it, but it is always possible to include that or factor also into the exponential, and then effectively then values of EA and this ED will somewhat change. That is about it. So, I will not include in my lectures right here. Okay. Now, next question is that if I want, okay, suppose temperature, now I have been saying that if the levels are shallow, is this EC, this is EV, if these levels are shallow, that means we are saying there is sufficient thermal energy that these electrons can jump in here. These electrons can jump in here, the electrons can jump in here also, the electrons can jump here at these levels, which means whatever acceptor I have added, all of it becomes ionized, and whatever donors I have added, they become ionized because they give their electron to the conduction band. What that means in this picture is when complete ionization occurs, complete ionizations occurs, then in that case approximately Nd plus by Nd is almost equal to 1, and Na minus by Na is almost equal to 1 is what we are saying. That means whatever we added, all that has ionized, because everything, all the electrons went in there, all the acceptors accepted the electrons and they became, so all the phosphorus atoms in silicon gave their 5th electrons away, so they became ionized. So, Nd plus value is same thing as whatever we have added. Similarly, if we have added boron, each boron atom has accepted, so therefore, Na minus is the same value as whatever we added. This is approximately equal to 1. So, you imagine like this, that this is a condition where we call as complete ionization. In that case, we can, in the next lecture, I will show you a problem, I will solve the problem of this complete ionization. Remember, at the end of the day, in intrinsic case, we have found what value of N and P are. We know that N is equal to P and its value is Ni, and Ni we have calculated, and I have shown you that. Now, when I have done the doping, I am again in thermal equilibrium interested in knowing what the value of N and P are. What is the value of N in number of electrons in conduction band, or what is the number of holes in the valence band? That is the number we are interested in. So, now when we have doped it, we are going to do it for 2 cases. Now, first case is when temperature is high enough, and therefore complete ionization occurs. All the electrons are able to, from donor levels, are able to go to conduction band. The electrons in valence band are able to jump to the acceptor level. In the next lecture, I will start with that and show to you in under complete ionization what the values of N and P are. Then what we will do is, we will start moving to low temperatures and see how, when the ionization is, when our assumption of complete ionization is not appropriate, that means ionization is incomplete, then what happens to N and P. Those are the 2 questions which we will answer in next 2 lectures. Thank you.